All right, folks, here's lesson 2-1. Here's some vocab words right here. A prime number. Okay, a prime number is a whole number greater than 1, but it has only two factors, 1 and itself. We'll talk about that in a bit there, okay? Now, the other type of number that's going to be in this lesson is composite. Okay, so here it is, composite. Composite number is a whole number greater than 1, but it's got more than two factors in it, and so that's the big difference. Okay? Don't worry, we're going to be going over it. Here's another thing I just want you to know. 0 and 1 are not prime and they're not composite. They're just kind of there. Okay? It's neither. All right? So let's go on down to this one. How do we know if a number is prime or composite? How do we know? Well, see if the numbers below are prime or composite and then explain why. So we have two numbers right here, and the first thing I'd like you to do is just let me kind of zoom in here. This is 2,727. If you went back to the first page of your packet, we have all the numbers between 1 and 1,000 telling whether or not it is prime. You'll notice that 1 is not prime. So anytime it's asking you that, you can go boom straight to this chart and you'd be like, is this prime? Okay? If it's bigger than 1,000, then we have to start thinking about this, the divisibility rules, right? And you could just go straight down. If you can prove that any of these big numbers are divisible by any of these, we're going to prove that it is a composite number. So can we divide this number by 2? Yes or no? Nope. So what's the rule to see if we can divide it by 3? What's the rule if we can see if we can divide it by 3? Add up all of the sum of the parts of the number there, just like that. What's 2 plus 7 plus 2 plus 7? What'd you all get? Very good, it's 18. And now if you go back to the sum, after you add them all up, ask yourself, is it divisible by what? 3. So is this 18 divisible by 3? Then I'm going to call this composite because divisible by what number? Because it's divisible by 3. So again, if we go back up to our definition, prime numbers have only two factors, 1 and itself. Composite numbers, they've got more than two factors. So if I looked at 2,727, would you agree with me that 1 times 2,727 is 2,727, right? So there's your two factors. And now if I divided this sucker by 3, right? If I divided this big old number by 3, we'd get 909. So if I times 909 by 3, we'd also get 2,227. How many factors do you see there, folks? I see 1, 2, 3, what? 4? That's proof that that is a composite number because it has more than how many factors? 2. So if you're looking for the easiest way of seeing if a big number is a composite number, see if you can divide it by any number that's not itself. If you can get a whole number answer without getting fractions and decimals, that's what it'll be. So can you guys go over there and try 15,482? Hopefully you guys were like, hey, this ends in a 2, so this is divisible by what? By 2. And you know, basically what we're talking about here is if I made a list of my factors, 1 times 15,482, we know that that is always going to start there, 1 and the number itself, right? But since it's divisible by 2, if I divided it, that gives me 7,741. 2 times 7,741. That is 2 more factors right there. Boom, 2 numbers that I can times together to get 15,482. So is this prime or composite? Prime or composite? Which one? Look at your definition. What is it? Composite. Yes. And so this is composite. So Mr. Tate, what about a prime number? What about a prime number? Well, let's come right over here and let's just look at the number 7 right up here, okay? I'm just going to kind of put a box up here. Folks, what can you What can you multiply to get 7? What are the two numbers you can multiply to get 7? 1 and 7. Can you think of any other two numbers, it's got to be whole numbers, that we can multiply to get 7? This is a prime number because these are the only two factors that we have. It's not divisible by 2, by 3, by 4, by 5, by 6, by 8, by 9. It is divisible by 7, but if I divide 7 by 7, what do I get? 1. And so, you know, it's no fair. You can't sit there and say divide it by itself. Look at 15,482. I can divide that by itself and we get 1. So that's the difference between prime and composite. You're just looking to see how can we divide it by. This one over here, though, just so you know, it's also divisible by the number 9. It's also divisible by the number 9. I don't feel the need to have us come through here and put it all together. But 18 is divisible by 9, and that's kind of how that rule works for the 9s. Again, though, the biggest thing that I want you to take away from this is that if there is a question that says, is this a prime number? And that number is between 1 and 1,000. Where should you look to go find it? On your what? On that first page of the packet, right? If it's bigger than 1,000, go see if you can divide it by one of these numbers. And if it's divisible by even just one of them, we know instantly it is composite. Does that help you out? Give me thumbs up or thumbs down, something. Okay. So at this point, let's move on to the next part. Prime factorization. Okay. Here's prime factorization. Prime factorization is where we have a composite number. That's what we were just talking about above. It's got more than two factors. Written as a product of, ooh, what's this right here? Prime numbers? Well, you've done this before. You really have. You may not remember it, but we're going to bring it back to you. How to find a prime factorization. Do you guys remember factor trees? Yeah. Write the prime factors in order. So let's come down here. This is what we do right here. 54. Could somebody tell me two numbers that you can multiply together to get 54? Nice. Now I would have gone with 6 and 9, but he said 2 and 27. If you want, you can come over here and put 6 and 9. You don't have to, but find two numbers that multiply together to get that number above. But here's the one rule that you can never ever do. Don't use the number that you're trying to get to. So in other words, if that's 54, don't use 1 and 54. Don't ever use the number itself, okay? Because all you're going to do is put down a 54 at a different level, and that's not going to help you break it down further. Now, guys, if you go back to the very, very first page, is 2 a prime number? So this is a prime number, and I want you to circle any prime numbers. See, that's a prime. You might even want to draw an arrow and go, hey, this is prime. You don't have to, but you might. Now, is 27 a prime number? Now, for my people that are like really bad with multiplication and stuff, you go right back here and you go, is 27 on here? Is 27? There's 23, there's 29. Correct. There's nothing between 23 and 29. So is 27 prime? Nope. So now we got to break this down, two numbers that we can multiply together to get 27. Wouldn't it be 3 times 9? Okay, well, what about 3? Is 3 prime? Yep, you can check your chart if you need it. You'll get used to it. What about 9? Is 9 prime? No. What can I multiply to get 9? 3 and what? 3. So my prime factorization of 54. I'm going to put 54 and I'm going to put a colon here. And now here's the key. I want you to write these prime factors in order. What's my smallest prime factor? 2. So write this one first and then say, hey, it's timesing, what's my other? 3 3s. And we're good with that. Now what happens every year though is that kids go, Mr. Tate, what happens if like I use different numbers than what you used, right? So our friend that said 2 times 27, this is what he got. 2 times 3 times 3 times 3. But me, I said I probably would have used 6 and 9. Guys, is 6 prime? No. What can we multiply to get 6 without using a 6? 2 and 3. And these are two prime numbers. Well, what about 9? Is 9 prime? No. So 3 and 3. Wait a second. Isn't this the same thing as that? And a lot of times this is jumbled up and it's not in order. If you're looking for a way to keep it neat, put your smallest one to the left and your bigger one to the right. So when I broke down 27 here, I put 3 to the left and 9 to the right. When I broke down 9 here, they were both equal, so it didn't matter which side. You don't have to, though, but if you're looking for a way to try and keep this neat, put the small one to the left and the bigger one to the right. Can you guys try 240? I'm going to pause it. Can you guys try breaking down 240 for prime factorization? All right, so I'm going to do this one two different ways, and there's a lot more than just these, but someone said, hey, what about 60 and 4? Well, great, these are not prime, so 60 I just broke down to 2 and 30, but the 4 broke down to 2 and 2, so these are primes, and that one's a prime, but 30, we got to break that one down. So, you could do 6 and 5, but I thought, what about 3 and 10? So 3 is prime, and then 10 is 2 and 5, so that's prime. And so literally what's happening here is that my 240 prime factorization is all of these circled prime factors. And we just got to put it together. How many 2's do we have here? 1, 2, 3, 4. So I want to start with my 2's first. And then I got 1, 3, and 1, 5. And again, all that we mean is that if you multiplied all these numbers back up together, you should get 240. How do you know if you got the prime factorization? If you multiplied all your prime factors back together, do you get the number that you started with, 240? And I also did this one a little bit messier because I just wanted to show you that if I'd put the things in a different way, like see, I always put my left small, right big, like that. But over here, this one kind of flip-flopped it out. If I'd flip-flopped these, it would have made it a little bit nicer. But if you'd use 10 and 24, you can break these factors down. Look, we still get 4 2's. 1, 2, 3, 4. 1, 3, and 1, 5. It's the same thing. Okay? All right, so your GCF, the greatest common factor. It's the largest number that's a factor of all the numbers. What are you talking about here? Well, if I said go find the GCF of 24 and 48, we've got two different numbers and we're trying to find the biggest prime factor. So like 240, the biggest, well, we're not going to worry about that too much. It's a little bit different, but we do have one little typo right here. Guys, can you scratch out 24 and 48? We're not going to find the GCF of 24 and 48. In fact, what we're going to do is we're going to show you two different methods, and it's your choice about which one you like better. Okay? You want me to show you the way that you probably did it in grade school? Let's go back and do that one. Here's 42. Hey guys, 1 times what? 1 times what is 42? Now that's what you always start with. You're like, hey, it's 1 and 42. So these are a pair. Now, can I times 2 and get 42? 2 times what? 21. Does that make sense? How many people are going, this is killing me here having to go back? Do you remember having the pain of this? Well, if you like the factor trees better, I can avoid the pain right here. Guess what? 3 is divisible into 42. 42 is divisible by 3. You can use that rule up. What's 4 plus 2? 6. So 6 is divisible by 3, so 3 times 14. What about a 4? Does a 4 work? 4 does not work. 5? No. What about 6? 6 and what? Now, the way that I stair-step this up, I know that once I get 1 and 42, my other options are 2 to 41. As soon as I say 2 times 21, I know the rest of my options are 3. What's less than 21? 20? So it's 3 to 20. Do you see how all of these are less than 3 to 20? As soon as I say it's 3 times 14, guess what? My other options are 4 to the number 13. And as soon as I say 6 times 7, is there any whole number between 6 or 7? Nothing. So that's it. Now let's come over here to 36. Let's say 1 times 36. That means that It could be, our next set of factors could be 2 to 35, right? It could be anywhere from 2 to 35. Can we times it by 2? Can we times something by 2 to get 36? 18? Well, crud. That gives us between 3 and 17. What about 3? Does 3 work? 3 and 12? What about 4 and 11? Can 4 work? 4 and 9? And then 5 to 8. Well, 5 doesn't work. Does 6 work? 6. Now, if you want to write a 6 over here on this column to show it 6 times 6, you can, or you can just leave it as 1. But these are all of our factors. And now we just come over here and we go, what's the biggest one between both of them? What's the biggest one between both of them? So your GCF, your greatest common factor between them, your biggest one that matches is 6. Okay? Now, this is it's an okay strategy. It's good, especially if you're good with your multiplication facts. If you're not great with them, this is what I'd rather you do instead. Come right over here. Do your factor trees. Do your factor trees and get your prime factorization like we did on method 1. Let's just do this. How about 4 and 6? 2 times 2 is 4, and these are prime. Does that make sense? Hey, what's 6 break down to, class? 2 and what? 3. Now, I want you to take the moment and just write down 24 and just write them 2 times 2 times 2 times 3. Your prime factors that all multiply together. We'll come right over to 60. We've got 6 times 10 because that's really easy, 6 times 10, right? Can we break 6 down, yes or no? 2 times what? 3. What about 10? 2 times 5. And so those are our prime factors. Come right down here and write them in order least to greatest. 2 times 2 times 3 times 5. So if you can get to the prime factorization using the factor trees and get them listed, then here's what is about to happen here. You circle all common factors and then multiply, okay? So you're going to circle all common factors and then multiply. So would you agree that they both have a 2 for prime factors, yes or no? So I'm going to circle it. So I'll be like, okay, that's a 2 times, do they have any other common factors? How about this set of 2? Okay, so we're going to put that one and say times it by 2. Do they have any other common factors on here that you guys see? 3. So now times it by 3. And they're not always going to be stacked up nice and neat on top of each other. Are we clear on that? Now, guys, what's 2 times 2 times 3? Your GCF is 12. Now, we're going to take a look at 63 and 84, and I want you to choose the one method that you feel most comfortable with. I'm going to use this prime factorization method right over here. Go do this right here. And in fact, you can follow along with me. I'll do this one in real time. I'll come over here and put the 84 over there. 7 times 9, 7's prime. 9 is 3 times 3, so prime. So I'm making a quick little note off to the side. These are the prime factors of 63 in order from least to greatest. And now I'm going to come over and work on 84 and get those least to greatest underneath this one. So that way then I can compare from my common factors. I know I can always divide an even number by 2. So 2 times 42, prime. 42 is 6 times 7. 7's a prime number, but 6 is not. That pulls us down to 2 times 3. And so now I can take all of my all of my prime factors for 84 and just list them least to greatest. And now I have to ask you guys a question. What are my common factors here? Does 63 have any 2's? No. Does So 3 and 7. So I can circle these right here. And again, guys, they're not always going to be stacked up, right? They're not always going to be stacked up. In this case, it is. Now, I'll rewrite my common ones. And so what do we do then after we rewrite our common ones? We just what? Multiply. So what is my GCF of 63 and 84? It's just 21. We're going to finish up with this last one right here, a story problem with GCF. Now watch. A parade director wants 2 bands to have the same number of people in every row. One band has 24 members, the other has 60. When it says, what is the greatest possible number? See right here, they ask, what's the greatest possible number? That is their way of saying, please use GCF. What are the 2 sizes of the bands there? We've got 24 and what? So all we got to do is go find 24 and 60, and we can do the exact same thing. I'm going to do my factor tree thing, okay? You should find prime factors of 2, 2, 2, and 3 for 24, and we've done 24 on this page before. In fact, if you go up here under method 2, there's 24. I used 4 and 6 that time. This time I used 3 and 8, but we're still going to get to the same prime factorization. Let's go through to the 60s. Oh, wait, guys, didn't we just do the 60 also over here? Huh. So I mean, really, we've done all of this before. I made a mistake there. I circled my 6 and 10 that were not prime. And so now let's just go and stack all of our numbers, line them up right here. 24 are common, 2 times 2 times 2 times 3. Here's our 60. We got 2 2s, 1 3, and a 5. And again, we just go through and we find our common numbers. Guys, what's 2 times 2 times 3? 12. So your GCF is 12. So what's this one? The greatest number of people in a row is what? What's our GCF? 12. So if they wanted like the marching bands to be the same width on the parade route, they'd say we need 12 in each row. That's your biggest one. If it's anything bigger than that, then you're going to have different sizes. But we can get everybody nice even rows of 12. And that's what's happening there. And that's the end of the lesson.